Letter 6 of Familiar Letters on Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Familiar Letters on Chemistry and its Relation to Commerce, Physiology, and Agriculture by Justus Liebig, M.D., Ph.D., F.R.S., Professor of Chemistry in the University of Gießen. Edited by John Gardner, M.D. Letter 6. My dear Sir, one of the most remarkable effects of the recent progress of science is the alliance of chemistry with physiology, by which a new and unexpected light has been thrown upon the vital processes of plants and animals. We have no longer any difficulty in understanding the different actions of aliments, poisons, and remedial agents. We have a clear conception of the causes of hunger, of the exact nature of death, and we are not, as formerly, obliged to content ourselves with a mere description of their symptoms. It is now ascertained with positive certainty that all the substances which constitute the food of man must be divided into two great classes, one of which serves for the nutrition and reproduction of the animal body, whilst the other ministers to quite different purposes. Thus starch, gum, sugar, beer, wine, spirits, etc., furnish no element capable of entering into the composition of blood, muscular fibre, or any part which is the seat of the vital principle. It must surely be universally interesting to trace the great change our views have undergone upon these subjects, as well as to become acquainted with the researches from which our present knowledge is derived. The primary conditions of the maintenance of animal life are a constant supply of certain matters, animal food, and of oxygen in the shape of atmospheric air. During every moment of life, oxygen is absorbed from the atmosphere in the organs of respiration, and the act of breathing cannot cease while life continues. The observations of physiologists have demonstrated that the body of an adult man, supplied abundantly with food, neither increases nor diminishes in weight during 24 hours, and yet the quantity of oxygen absorbed into his system in that period is very considerable. According to the experiments of Lavoisier, an adult man takes into his system from the atmosphere, in 1 year, no less than 746 pounds weight of oxygen. The calculations of Menzies make the quantity amount even to 837 pounds, but we find his weight at the end of the year either exactly the same or different one way or the other by at most a few pounds. What, it may be asked, has become of the enormous amount of oxygen thus introduced into the human system in the course of 1 year? We can answer this question satisfactorily. No part of the oxygen remains in the body, but is given out again, combined with carbon and hydrogen. The carbon and hydrogen of certain parts of the animal body combine with the oxygen introduced through the lungs and skin, and pass off in the forms of carbonic acid and vapor of water. At every expiration and every moment of life, a certain amount of its elements are separated from the animal organism, having entered into combination with the oxygen of the atmosphere. In order to obtain a basis for the approximate calculation, we may assume, with Lavoisier and Séguin, that an adult man absorbs into his system 32½ ounces of oxygen daily, that is, 46,037 cubic inches, equal to 15,661 grains, French weight, and further, that the weight of the whole mass of his blood is 24 pounds, of which 80% is water. Now, from the known composition of the blood, we know that in order to convert its whole amount of carbon and hydrogen into carbonic acid and water, 64.102 grains of oxygen are required. This quantity will be taken into the system in 4 days and 5 hours. Whether the oxygen enters into combination directly with the elements of the blood, or with the carbon and hydrogen of other parts of the body, it follows inevitably, the weight of the body remaining unchanged and in a normal condition, that as much of these elements as will suffice to supply 24 pounds of blood must be taken into the system in 4 days and 5 hours, and this necessary amount is furnished by the food. We have not, however, remained satisfied with mere approximation. We have determined accurately, in certain cases, the quantity of carbon taken daily in the food, and of that which passes out of the body in the feces and urine combined, that is, uncombined with oxygen. And from these investigations it appears that an adult man taking moderate exercise consumes 13.9 ounces of carbon, which pass off through the skin and lungs as carbonic acid gas. Footnote 1. This account is deduced from observations made upon the average daily consumption of about 30 soldiers in barracks. The food of these men, consisting of meat, bread, potatoes, lentils, peas, beans, butter, salt, pepper, etc., was accurately weighed during a month, and each article subjected to ultimate analysis. Of the quantity of food, beer, and spirits taken by the men when out of the barracks, we have a close approximation from the report of the sergeant, and from the weight and analysis of the feces and urine, it appears that the carbon which passes off through these channels may be considered equivalent to the amount taken in that portion of the food, and of sauerkraut, which was not included in the estimate. It requires 37 ounces of oxygen to convert 13 9/10 of carbon into carbonic acid. Again, according to the analysis of Boussingault, a horse consumes 79 1/10 ounces of carbon in 24 hours, a milk cow 70 3/4 ounces, so that the horse requires 13 pounds 3 1/2 ounces, and the cow 11 pounds 10 3/4 ounces of oxygen. Footnote 2. 17.5 ounces equals 0.5 kilogram. As no part of the oxygen taken into the system of an animal is given off in any other form than combined with carbon or hydrogen, and as in normal condition or state of health, the carbon and hydrogen so given off are replaced by those elements in the food, it is evident that the amount of nourishment required by an animal for its support must be in direct ratio with the quantity of oxygen taken into its system. Two animals which in equal times take up by means of the lungs and skin unequal quantities of oxygen consume an amount of food unequal in the same ratio. The consumption of oxygen in a given time may be expressed by the number of respirations. It is therefore obvious that in the same animal the quantity of nourishment required must vary with the force and number of respirations. A child breathes quicker than an adult, and consequently requires food more frequently and proportionably in larger quantity, and bears hunger less easily. A bird deprived of food dies on the third day, while a serpent, confined under a bell, respires so slowly that the quantity of carbonic acid generated in an hour can scarcely be observed, and it will live 3 months or longer without food. The number of respirations is fewer in a state of rest than during labor or exercise. The quantity of food necessary in both cases must be in the same ratio. An excess of food, a want of due amount of respired oxygen or of exercise, as also great exercise, which obliges us to take an increased supply of food, together with weak organs of digestion, are incompatible with health. But the quantity of oxygen received by an animal through the lungs not only depends upon the number of respirations, but also upon the temperature of the respired air. The size of the thorax of an animal is unchangeable. We may therefore regard the volume of air which enters at every inspiration as uniform, but its weight, and consequently the amount of oxygen it contains, is not constant. Air is expanded by heat, and contracted by cold. An equal volume of hot and cold air contains, therefore, an unequal amount of oxygen. In summer, atmospheric air contains water in the form of vapor. It is nearly deprived of it in winter. The volume of oxygen in the same volume of air is smaller in summer than in winter. In summer and winter, at the pole and at the equator, we inspire an equal volume of air. The cold air is warm during respiration and acquires the temperature of the body. In order, therefore, to introduce into the lungs a given amount of oxygen, less expenditure of force is necessary in winter than in summer, and for the same expenditure of force more oxygen is inspired in winter. It is also obvious that in an equal number of respirations we consume more oxygen at the level of the sea than on a mountain. The oxygen taken into the system is given out again in the same form, both in summer and winter. We expire more carbon at a low than at a high temperature, and require more or less carbon in our food in the same proportion. And consequently more is respired in Sweden than in Sicily, and in our own country an eighth more in winter than in summer. Even if an equal weight of food is consumed in hot and cold climates, infinite wisdom has ordained that very unequal proportions of carbon shall be taken in it. The food prepared for the inhabitants of southern climes does not contain in a fresh state more than 12% of carbon, while the blubber and train oil which feed the inhabitants of